Graphical Transformations. In this video, we'll be looking at transformations, vertical and horizontal translations, reflections across axes, vertical and horizontal stretches and shrinks, and combining transformations. We'll be looking at two different kinds of transformations: at rigid transformations that leave the size and the shape of the graph unchanged, and non-rigid transformations, which generally distort the shape of the graph, including horizontal or vertical stretches and shrinks. Let's start by looking at the function y equals x squared. I have graphed on the calculator a couple other functions. The first one is y equals x squared. The next one is x squared plus 3. If you notice that I do not have all three of them selected. To select a graph to have it shown, we want the equal sign to be highlighted. I've also, on the left-hand side, selected different shapes for the individual graphs. So the first one that was being shown was just y equals x squared, and that's what this graph is. Now if I want to also add the second one, I'll use my arrow key and then enter, and it will highlight this one, which is in the darker line, x squared plus 3. So we're taking our original function, x squared, and we're going to add 3 to it, and that's what we get. Now we'll go back and add the next one in, x squared minus 2, and graph that. So you can see what this is doing to our graphs. The original one is in the middle of the x squared, x plus 3 is the one in the dark, and the bottom is x squared minus 2. Let's do the same thing again with some different transformations. Again, here's the x plus y equals x squared. And now we're going to look at x plus 3 quantity squared. So we'll activate that graph, and we can see that it's shifted to the left. And when we do the x minus 3 quantity squared, and graph it, we can see that it's shifted to the right. Try these things yourself. Try the transformation with y equals the absolute value of x and y equals the square root of x. Try adding 3 and subtracting 2 both within the absolute value and without, and within the square root and without, and see if the same properties apply. So here are the rules for the vertical and horizontal translations. If we start off with some function y equals f of x, a horizontal translation, the horizontal translations occur within the parentheses. So x minus c and x plus c are within the parentheses, and it is the opposite. So when you subtract c, lost my pen there. When you subtract c, you translate to the right by c, and when you add c, you translate to the left by c. The vertical translation is outside of the parentheses. So outside of the parentheses, when we add c, we go up c, and we subtract c, we go down c. To show you how this works, we're going to take the graph of f of x equals the absolute value of x, which is our v graph. So it looks something like that. And we're going to transform it to the absolute value of x minus 4. Now the minus 4 in this case is outside the parentheses or the absolute value. So it's going to be a translation on the y. So all we do on that is we go down 4. 1, 2, 3, 4, and we would draw the same graph. And both those lines, all those lines would continue. So that's the function and its graph. Very rough sketch, but it gives you an idea of how those work. We can also work backwards and find equations for translations. If we are given the basic function and the graph, we can figure out what the equation is. So here we have the graph of y1 equals x cubed. In the first situation, we are taking the graph and moving it down along the y-axis. So because we're moving along the y-axis, the equation for this will be x cubed and we've taken it and we've gone down 3, and because it's outside the parentheses with the y, it's the same sign. We go down 3, so it's negative 3. This one, we have y is equal to, now we're going left and right, so it's going to be inside the parentheses, and the sign is opposite. So this is x plus 3, and all of that is cubed. And on this one, again, it's the y is equal to x minus 3 quantity cubed. Now we will look at reflections. If we are reflecting something across the x-axis, we take the opposite or the negative of the entire function. If we are reflecting it across the y-axis, we're going to take the opposite of the x. I'll show you how that works when we find the equation of the reflection of f of x equals 5x cubed plus 3x squared minus 2 across the x-axis and across the y-axis. So across the x-axis, we're going to take the negative of the function. So that would be the negative of the entire function, 5x cubed plus 3x squared minus 2 gives us a negative 5x cubed minus 3x squared plus 2. Across the y-axis, we take f of negative x. So that would be equal to 5 of negative x cubed plus 3 negative x squared minus 2. We have a negative cubed. We retain the negative, so it's negative 5x cubed plus 3. When we square a negative, it becomes positive 3x squared minus 2. We're going to look at some stretches and shrinks. This graph is a function of the square root of 4 minus x squared. I'll show you the formula for that. 4 minus square root of 4 minus x squared. I'm going to take that function and multiply it times 1.5. So it's 1.5, 1.5 times the square root of 4 minus x squared. So I'll go ahead and activate that graph. And you can see it stretched it a little bit more. And if I activate the next one times 2, it'll stretch it even more. So multiplying a graph times a factor greater than 1 will stretch it out. If I was going to multiply it times a number less than 1, 0.5, second square root, and graph that, it'll shrink it down from where it was. Now let's look at the same graph. I've zoomed in a little bit and see what happens when we put the multiplier inside the parentheses. So here's our original graph, which was the square root of 4 minus x squared. I'm going to head and activate the next one where I have 4 minus 1.5x squared. And we can see that it's squeezing it in left to right. Inside the parentheses deals with the x value. Outside of the parentheses deals with the y value. So activating this next one where we have 2x it squeezes it in even more. And this time I was better prepared. On 0.5x, activating that one, so I'm multiplying by a factor of less than 1, and it stretches it out. So greater than 1 is going to squeeze it in, less than 1 will stretch it out. So here it is written out, where we have horizontal stretches and shrinks. If we have it a factor within the function, it's going to stretch it or shrink it horizontally. And if the vertical stretches, if it's outside of the function, it's going to stretch or shrink vertically. So putting that knowledge to use, we've got our function y1 equals x cubed plus 3. If we want a vertical stretch by a factor of 4, that the vertical stretch is with the y's and it's going to be outside the function, so it's going to be 4 times x cubed plus 3, which using distributive property gives us 4x cubed plus 12, and that will be a vertical stretch by a factor of 4. C3, horizontal shrink by a factor of 1/3. Now this one's a little confusing because you're thinking shrink, okay, that's shrinking 1/3, it's making it smaller, but when you're shrinking, you're actually dividing. So this is, let's try that again, I get the draw going. When you're shrinking, you've got x cubed divided by 1/3 plus 3. And when you divide by 1/3, you're actually multiplying by 3. So we get 3x to the third plus 3. Let's combine some of these transformations in order. If we take a graph of y equals x squared, and we want a horizontal shift of 5 units to the left, we have y is equal to horizontal. It's on the x, so it's inside the parentheses, and it's opposite. So we go x plus 5 squared. That's 5 units to the left. Then we have a vertical factor of 3, a vertical stretch by a factor of 3. So that's on the y, that's outside, and that's a multiplication. 3 times x plus 5 squared. And then a vertical translation 4 units up, that's outside. And it's y equals 3 times x plus 5 squared. It's on the y, it's going up, so it's up 4. Now you try it. Take the same function, y equals x squared, and the transformations in the opposite order, and find the equation of the graph that results. And I leave you with this just for fun. Let them figure out how much